Yes. Actually, what happens with Zoom is that we have to interrupt the session after every 40 minutes. So, can you please join Google Meet? There we can have one session for the entire 2 hours.
Okay. So we can leave from here.
Yes, you can leave from here and you can join Google Meet. And once everyone has joined, you will start. Um, Hello, Subhadra. Can you please join this Google Meet link? Okay, I think you've already joined. So, okay, then we can start.
Recording stopped.
Hello everyone, are you able to see the screen? Hello, is the screen visible? I think it should be. Hello everyone, welcome to this problem session for the week 4. Today we will be talking about neural networks. So the outline of the session will be, we will start with the perceptron algorithm followed by the backpropagation, and then we will look at two hidden layer neural network. We will also look at its implementation in PyTorch. Starting with perceptron. Okay, so X here represents an input and Y is the output. Okay, so now suppose you have an input X and g of x is basic. So we have defined a function which is some function of g of x itself as an output y here. So this function, so the value of y will be equal to 1 if this g of x is greater than or equal to say some angle theta, and if g of x is less than some threshold theta here, then it will be 0. So theta is serving here as a threshold, and based on that threshold and the value of g of x, the decision is being made whether x should be assigned a label of 1 or 0. So here looks at it visually. Like if you look at this graph, you'll see that there is this input x. Now x can be a high dimensional input, and suppose there are n dimensions, it's an n dimensional input. So what will happen, we will give this n dimensional input to a function, and let's for now assume that g of x is written as w transpose x, which means for I equal to 1 to n, it's wixi plus some bias term. Okay, this can be represented by further can be represented as I equal to 0 to n summation of wixi, where w0 will be this b and x0 will be 1. Okay, now if you fit this thing, if you look at this particular equation here where we say y equal to f of g of x, and this is being 1 if g of x is some greater than some threshold theta, then you can see that w naught here is nothing but negative theta, right? Because see, if this is our g of x, okay, and if this g of x is greater than equal to theta, which means g of x minus theta should be greater than equal to 0, right? And that minus theta is nothing but representing this b here. Okay, so that's how the threshold is coming directly into the equation of the perceptron. So given any input x, we can have certain weights w, using which we will get some value, and applying some threshold on that value b, we can have a classification decision made. Okay, if we are adding a bias, then we do not need a specific threshold, and we can directly have the decision there. Okay. So now this is what perceptron is. So suppose if you get an input x and the w which you have learned so far, and according to that w, the decision you make for this x is correct, then this w will remain unchanged. But if the decision for new x is not as you are expecting, then the w will be updated accordingly. So suppose, okay, also one thing note here that this y, which is defined as a function of g of x, is assigned a label of 1 if g of x minus theta, which is nothing but this I equal to 1 to n wxi xi plus b minus theta is greater than or equal to 0. So you can also see that here we are just making a decision based on the sign of this function, right? So if the sign of the function is positive, then we are assigning it a value of 1. If it is negative, we are assigning it a value of 0, right? If you take theta here to be 0, then you can, it's a simply sign based decision. And just changing like considering these two equations to be same, you can see that b is here nothing but minus theta. Okay, and that can be represented as x0 into w0, and that's what I meant when we can have from I equal to 1 to n, instead of this I equal to 1 to n, we can also represent it as I equal to 0 to n wxi xi, where x0 will be the 1 because this is like, this is just done for simplifying this expression further. So we are adding one more dimension to the input but keeping it a same value of 1 fixed, so that we can have just represent this equation by simply w transpose x. Okay, this is more to simplify the computation but nothing more than that. Okay, okay, so what is perceptron is doing? So basically the idea is that we have to find a line, a hyperplane in high dimension, which can divide the input space into two halves. And we are talking about binary classifiers, and that's why we wanted to divide the input space using the slurred hyperplane into two halves, where each half will be representing one specific class. And w transpose x equal to 0 will be the So this is representing your hyperplane, and all the points which will be satisfying this equation will be lying on this hyperplane. Okay, so these four are the x which are lying on the line or the hyperplane itself. So suppose this is the hyperplane here, and these are the points which are satisfying this w transpose x equal to 0. So that means the angle between w and these points lying on the hyperplane has to be 90 degrees. That's why your w is being shown as a normal to this line, right? Now, this W transpose X can be written as just expanding the dot product formula. So it will be norm of W into norm of X into cos alpha, where alpha being the angle between W and X. And this will be 0, like this dot product will be 0 only if this cos alpha is 0, which happens when alpha is 90 degree, provided that neither W nor X is 0. Okay, so this is how this perceptron algorithm works. Okay, and now suppose there is an x which belongs to some positive class p. X belongs to positive class p means that y will be assigned a label of 1. In this case, what we want that this w transpose x should result in a value which is greater than or equal to 0. Expanding the dot product formula, we will get norm of w into norm of x into cos alpha should be greater than or equal to 0. Now, norm of w will be a positive quantity, norm of x will be a positive quantity. So for this entire expression to be greater than or equal to 0, so equal to 0 is basically just lying on the hyperplane, and you can assign it to either of the classes. But if you strictly want it to be assigned a label 1, then it has to be strictly greater than 0. In either case, this cos alpha is deciding the actual decision here, right? So if the cos alpha is positive, then this particular input x will be assigned to the positive class p. If cos alpha is negative, then x will be assigned to the negative class, that is y will be assigned a value of 0. Okay, now if you talk about cos alpha, so cos alpha will be positive if alpha is less than or equal to 90 degree, right? Similarly, if x belongs to negative class, then we want y to be assigned a value of 0, which means the dot product of w and x should be less than 0, which means cos alpha has to be negative. Okay, so depending on the angle between the input x and the w vector here, we can assign an input x to either class labeled as 1 or 0. Okay, now how do we do the model update? So far we decided that okay, if we know w, then this is how we will be taking a decision. But the important question is, how do we know this w? So for that, we will now this is how we can update w. So if x of t belongs to p, okay, and so it means that the label for x here is 1. But what is happening that given the w, that there is a misclassification, which means that though this x of x belongs to positive class, it is being predicted as an instance of a negative class. Then we have to update w to minimize this error, right? Which means, so what is the reason that this w transpose x of t is less than 0? The reason is that the cos alpha is negative. Okay, so how should we make sure that this x should be correctly updated by updating the w? What should be done? The idea is that since this is negative, this is less than 0, we have to push it towards the positive side, right? So for that, the update has to be done such that whatever the w new is, its dot product with this input x should definitely be greater than the output of the dot product of the current w with x. This is clear. We are doing this because x belongs to a positive class and it has been predicted as an instance of a negative class. So to reduce this error, we have to increase the value of this dot product, and that's how the w should be updated. Okay, so this w new is w plus x of t. Okay, and what will happen here? So just consider this, right now. What if we just add to this thing that we have this w of nu is equal to w plus x of t? We just add that x to w itself, okay? Then what will happen? W nu transpose into x will be w, just substituting this value for w nu here and computing the dot product, okay? So this is our initial dot product which we had with the current estimate of w plus a norm of x of t. Now this term will always be greater than 0 unless x is a 0 vector. In that case it will remain unchanged. That means w nu transpose x will be same as w transpose x, but otherwise this value will always be positive if x is a non-zero vector. Okay, so which means that this w nu transpose x of t is greater than or equal to w transpose x of t, and this will be strictly greater than w transpose x if x is not equal to 0. Okay, now to look at it, what is actually happening, to visualize it, suppose this is your initial w. Okay, so we have to update the hyperplane such that x of t after update is classified as a member of positive class p. Now this is the input x of t, this is the initial classifier w, okay, and this is where the positive class p is. So ideally what we have to do to include x of t as an instance of a positive class, this hyperplane has to be rotated by certain degrees such that this x now lies on the positive side of the hyperplane. And that's why you'll see that with each update, this hyperplane is shifting to accommodate each misclassified input to its actually correct side of the plane. Okay, that is what is happening here is this thing. So initially this was the angle between it, right? So if you plot, this was the angle alpha. Okay, the angle between x and w, let's call it alpha, and the angle between w nu and x, let's call it alpha nu. So if you see this equation, it says that w nu transpose x of t is greater than w transpose x of t, and if you just apply the simple dot product formula, it will be norm of w into norm of x into cos alpha nu, and this will be norm of w into norm of x into cos alpha. Okay, which means that cos alpha nu has to be greater than cos alpha if we put a constraint that the norm of w nu and w will remain the same. Okay, so substituting it and solving it, you will get this cos alpha nu, which is simple the dot product formula, that is the dot product of w transpose with x divided by the norm of w nu and x. So this is your cos alpha nu, and so why this equation came, that's clear, right? Because we are assuming that we are making sure that the norm of w is same, which means norm of w is same as the norm of the updated w, and so on, which is always 1. So what is changing is actually the angle. The rotation of the hyperplane is what is actually getting updated in this perceptron. Okay, so here it will become w transpose x of t plus norm of x of t upon divided by norm of w nu into norm of x, okay, which is equal to, so this term is nothing but cos alpha, right, plus norm of x of t. Because this square will cancel with this, so we will left with only one norm of x of t, and this norm of w nu is nothing but 1, which means this cos alpha nu is definitely greater than cos alpha because of this added positive term, which means the angle has been reduced, and that's what is being shown here. So initially the angle between this x and w was large, and the angle between x and this updated w is less. Okay. Okay. So any questions so far on perceptron? Okay then, moving on to the next topic, which is backpropagation. So far we are doing this perceptron algorithm, and can anyone suggest what is the issue with this algorithm here, perceptron? Is there anything on the chat? Okay, I don't see anything on the chat. Okay. So the problem with Perceptron is that it is susceptible to outliers. So if you give one noisy input, the Perceptron algorithm will make sure that the hyperplane or whatever the hyperplane we are learning is updated to even adjust this outlier. So if we have lot of outliers in our algorithm, or even if we have a very small number of it, they are definitely going to affect this hyperplane. So the robustness to noisy inputs is very less in perceptron algorithm. Uh, Now moving on to the next thing, which is backpropagation, which works in an end-to-end fashion. So this algorithm forms the basis of all neural networks and all deep learning based architectures. So please focus on this. And if you have any questions at any point, uh, feel free to mute or unmute yourself and ask. Okay. Now suppose we have a training data T, which comprises of n labeled inputs. By labeled inputs, I mean that we have an input x1 and we also know its correct label or correct output as y1. Okay, so this is an example of a supervised learning where each input is annotated with its ground truth value. Now we have a neural network, let's say. Okay, so here we can see that there is a two-layer neural network. Basically, what is happening? There is one hidden layer here. This is an input layer, and that's okay. Sorry, there are two hidden layer uh, neural network. This is being the input layer, and that is the output y. Okay. So, given any input x, x1, x2, x3, and here we are considering a three-dimensional input. So we give an input x1, x2, x3. We pass it through this layer. So what it will be? So the output of this layer, okay, will be w1 times of x plus b1, similar to perceptron, right? See, so similar to this equation, we have this equation for each layer. So this is also known as multi-perceptrons algorithm, okay? Multiple perceptron layers. So we have this w1x plus b1, okay? And then we have some nonlinear function sigmoid, okay? Then comes the another layer u2, for which what will be output is defined as u2, which will be this u1 will serve as an input to this second layer, okay, and the output of this layer will be w2 times u1 plus b2, and then applying some activation function sigma here, okay. Then the output is u2. Again, this u2 will be passed as an input to the third layer, and the output will be w3u2 plus b3, which is equal to the output of the model x, and it can also be represented as the predicted value of x, okay. So this is the basic neural network architecture, where the output of one layer is serving as an input to the other layer, and so on. The output of each layer is being followed, is being passed as an input to some non-linear function, uh, and then only it is being passed as an input to the consecutive layer, okay. So we have a ground truth value for each input x, okay. So for x1 we know the ground truth value is y1, for input x2 the ground truth value is y2, for input xn the ground truth value is yn, and so on. Similarly, for each input we have a predicted value as yp. Ideally we want this predicted value to be as close to the ground truth value y. So this intuition will help us in forming a loss function. So a loss function is defined as some function of the predicted output yp and the ground truth output or the desired output y. Assume for now f to be a mean squared error. So this is a regression setting where each input x is being labeled with some real value, and the model is predicting some real value as well. The goal is that the predicted real value should be very close to the ground truth real value. Okay, so this is a case of regression. Okay, the example could be, suppose uh, there is a history of a company, uh, history of the stock price of the share price of the company, and then you have to predict the share price in the next year. Okay, so this can be one example of a regression task where the input can be high dimensional depending on the number of years you are taking as an input, and the output will be a single value, which will be predicting the what is the more likely value of the share, maybe in the next month or year, and so on. Okay, so assuming f to be a mean squared error function here, we can define f of yp comma y as yp minus y and its L2 norm. Okay, this half is being added here because during differentiation it will help us in simplifying the expression. Uh, Sometimes we can have other constants here, maybe some lambda. So the loss function can be lambda times of this, where lambda can be anything which can either be decided based on some prior knowledge or can be learned by end-to-end backpropagation as well. Okay, now using this loss function, we will see how to update the weights of each layer. Okay, so in neural network, the idea is that given this data, the input data and output data, we have to find the right weights and biases for each layer and neuron in the network. And this is being done by optimizing this loss function. By optimizing, I mean we have to minimize the value of this loss function. The smaller the value of the loss function is, the good the network is. So talking about the last layer, now this loss function L is defined as 1 by 2 L2 norm of yp minus y, and this yp is defined as w3u2 plus b3. Okay, so we will start from the last layer. So we will first try to find the update for weight w3, followed by the update for b3, and we will use this equations to find the update for w2 and b2. Then we will use these equations to find an update for w1 and b1, and so on. So finding the derivative of L with respect to W3 will be simply differentiating this loss function with respect to yp and then differentiating yp with respect to W3, the chain rule. Okay, so derivative of L with respect to yp is yp. Okay, and derivative of yp with respect to W3 is u2. So the gradient of the loss function with respect to weight W3 is just being given by yp times of u2, and u2 is nothing but the input to the layer itself. And similarly, the gradient of loss function with respect to bias b3 will be derivative of loss function with respect to yp into derivative of yp with respect to b3. So derivative of loss function with respect to yp is yp, derivative of yp with respect to bias is 1, right? So derivative, so this turns out to be just yp. Now these equations will be further used to calculate the gradient for other weights. So for this second last layer, we will have derivative of L with respect to W2 is equal to derivative of L with respect to yp into derivative of yp with respect to u2 into derivative of u2 with respect to W2. Clear? So we know the value of this thing. This is nothing but derivative of L. So this is nothing but yp into W3 into derivative of u2 with respect to W2. Now for this thing, if you see, there is also this non-linear function. So u2 is defined as some function of w2 u1 plus b2. So when you will go and differentiate u2 with respect to w2, we have to first differentiate this function and then we have to differentiate this expression. So it will be written as derivative of the sigmoid with respect to w2 represented as sigma prime here with the same argument into derivative of the argument with respect to w2. Okay, so it will be sigma prime of z into a derivative of z with respect to w2, where z is representing w2 u1 plus b2. Now, what will be the derivative of sigma? Right, sigma can be any nonlinear function. So suppose sigma is a sigmoid. If sigma is a sigmoid function, then this is represented as 1 upon 1 plus e to the power minus c. And the derivative of sigmoid function is equal to e to the power minus c upon 1 plus e to the power minus c and the whole square of it. In case sigma here represents a Rayleigh function, then it is defined as sigma. The Rayleigh function for z is defined as the maximum value, maximum of 0 or the argument itself, which is z, and its derivative will be if the maximum value selected is 0, that is the argument z here is negative, then this will be 0, otherwise it will be 1, and so on. So it can be a Rayleigh, sigmoid, 10h, leaky Rayleigh, exponential Rayleigh. It can be any nonlinear activation function. Depending on what function it is, you have to compute its derivative accordingly. Okay, so what will happen now? Once you know what is the derivative of the activation function, you can compute and fit it here, and then you can compute the derivative of this with respect to z or w2, which is nothing but u1 itself. Multiply that and you'll get the derivative of u2 with respect to w2. Similarly, what will be the derivative of u2 with respect to bias? It will be only sigma prime z. Okay. Okay. So similarly, you can compute it further for the first layer, which is u1, which is using u2 as an input. Which is serving as an input for the second layer. So similarly, you can compute for u1, and in that case, it will be derivative of L with respect to yp into derivative of yp with respect to u2 into derivative of u2 with respect to u1, and then it will be derivative of u1 with respect to w1. So that will give you the update for the weights of the first hidden layer, and so on. Okay. So any questions on this backpropagation algorithm? Any questions on chat? Okay, so there is a comment, only binary classification. So what do you mean by this statement, Yash? Hello?
Ma'am, I was referring that perceptrons can only be used for binary classification.
Yes, so this is because we are just using it for two classes, right? We are just saying that if the input is on the positive side of the hyperplane, then it is assigned a label of 1. If it is on the other side of the hyperplane, then it is assigned a label of 0. But you can extend it for multi-class setting by learning perceptron for each class independently, right? So suppose there are 3 classes. Now labeled as class 1, 2, 3. So for class 1, it will be only whether it belongs to class 1 or not. For class 2, it can be whether it belongs to class 2 or not. Similarly, for class 3, it can be whether it belongs to class 3 or not. So you can have 3 binary classifiers to do this multi-class classification.
Okay, ma'am.
Okay. So any doubts in perceptron or backpropagation algorithms? If not, we will move to implementation part. So before starting with here, I'll just want to do a small example, and then we will talk about the neural networks implementation on MNIST dataset. So let's say that we define a function y which is x square plus 4. Okay, and x is some random input we take from numpy. Or maybe I can just assign it some value. So let's say I assign it some value of
Ma'am, you will have to map the function to uh, you will have to map the y function to the x.
what do you mean by map here? Hello?
Ma'am, aren't we plotting the y function on the x values?
We are plotting the y function on the x value cs. So that's what we have done here, right? So for -4 you will see a value of 20, and that's what it is showing here. So
Yes, ma'am.
it's a one-dimensional data, okay? So that's why we are showing a 2D plot. Now I can also do it like this. Maybe I can have np.linspace, and let's say we take the range of -10 to 10, and we sample 100 inputs, okay? So now you can see that this is more smooth, right? This looks like a quadratic function. Okay. Now the goal is that given this input x and y, we want to have a small neural network which can predict this value y. Okay. So let's create such input. So we have w1, which is, maybe we can assign some random values here. So what should be the, what you want to be the, maybe we can do it with, let's say for the first layer we have a dimensionality of 4. Okay, and we just work with one single layer. So let me assign it some random values initially, which is three. And this also, maybe we can just assign it to be a 0 here. Okay, so this is in our initial field vector w1 and p1. And let's say we define by p as w1 times x plus p1 let's call it u1, okay, and some function of this. So what should be the function? So we can define a function here. Define support c equal return 1 divided by
Ma'am, I guess you have to import math library also for the exp function.
for the xp function what? Okay,
Import math.
yeah, in fact you can do np.xp also. Okay, so what you want? Shall we keep it just to two layers for right now so that we can understand it, and then we can go ahead. Okay, so the first layer is taking an input x, multiplying it with segment and passing it. And the second layer only had w2 and u1, let's say. So it's still w2 times of u1 comma b2. Okay, and this is what your predicted output is, let's say for underscore p. This is clear. Now our input is a dimensionality of 1. Now suppose we have this input here, okay, and let's say we take all the input. So the dimensions, so the shape is 100 comma 1, and here we will multiply it with 1 comma 3. So I'm converting it to matrix multiplication so that we can pass it the entire batch now instead of just doing it one for input. Okay, that's clear, right? So now you can see here that, let me squeeze it. So we are just visualizing how it looks and how the raw input looks. Okay. So if you see here on this scale, this is the prediction which you are getting for your actual ground truth. Okay, and this is the value which you are getting for these random values we have assigned right now. Okay, so the idea is that we have to first update this W so that we can match this orange curve and the blue curve here. Okay, so for that, what we will do is we have to update it. So will you tell me how to update this equation? Like, anyone who would like to volunteer?
We will use the loss function.
Okay, and what will be the loss function?
Half of square of difference.
Defining loss value is y comma y underscore p. What it will be? Written
Square of difference.
y minus y underscore p into y minus y underscore p 0.5 into this. Is that okay? So we will get the loss, and let's say we also want the loss value here. So loss is equal to loss underscore 12 y comma y underscore p, and let's print loss as well. So this is the loss value, right? Can anyone tell me why this is like so many values here?
We have used np dot line space. It takes 30 values.
It is taking 100 values, I think. We took 100
Yes, sorry,
samples, right?
100 values.
Yeah, so now we have computed the loss for each input. However, when you were back propagating, we needed a scalar value, right? Not a vector. So what we can do is we will sum it up. So here the loss value will be np dot sum of this. And this is your loss, which is very big. Okay. So now let's try to update the loss function.
Why do we multiply it with half?
Okay, because when you were differentiating here, yes, so when you take the derivative of L with respect to this yp, you get this 2 here. So just to cancel it out, we are using half there to simplify the equation.
Okay, ma'am.
So now we need to write the update equation for in a reverse order. So what will be the update equation for W2? Anyone would like to say something? So it will be yp into this value here, which is u1. Remember? So it will be y underscore p dot reshape, and you can just write reshape it into 1 comma minus 1 into the value of u1 here. Okay, now this might seem tedious to you, like how to update and all. So for that, if you do not want to write, okay, I'm doing this equation just to explain you how to code it from scratch. But in case you directly want to move on to torch, you can even call the torch here like PyTorch and simply use its autodiff to get these gradients and update it. Okay, which we will be looking in the second half. So does this make sense to you? So this is similar to what we had on the slides, right? So derivative of u2 with respect to value. Yes, so this is similar, right? Yp into u2, right? So that's what we are doing here. Sorry, yp into u2. Okay, clear? And the output of u1 here will be having a dimensionality of. Okay, first let me help you in writing the dimensionality. So this dimensionality is 100, 1. So there are 100 inputs, each input is of 1 dimension. Okay. The shape of y is 100, 1 again. So here it is 100 only. It's better like this, but later on we are reshaping here. What is the shape of w? 1, 3. Shape of y is 3. Shape of w2, 3, 1. Shape of p2, 4. Now here, what is the shape of u1? And shape of yp? So with this, the loss value is, let's reshape it as well. Okay, cool. So when we are updating file w2, the update has to be in the shape of w2, and the shape of w2 is 3 cross 1. So are we getting the similar shape? So we have reshaped by p. We don't need to reshape it. Actually, we need to take the transpose of it. So you can actually take a transpose as well, or you can do it that way, like whatever works. So you can even take a transpose there. Maybe for simplicity, we can write transpose here. Okay, so now if you try to do this, you will get the update for W2 gradient and B2 gradient, and then once you have the update, you will try to update the weights W2 and B2 itself, which will be computed as, so this is gradient of W2, and the update will be W2 is equal to W2 plus whatever is the learning rate into W2 grade. And okay, and then you can similarly write the equation for layer 1 and can keep on updating it. So what will happen is that eventually this orange curve will start reshaping it as this blue curve. Okay, uh, so once you have written the equation for W2, so this is the equation for W2 and B2, right? Similarly, you can write the equation for W1 and B1 as well, and then you can keep on doing it in loop. So what will be the loop look like? So the loop will be, suppose you want to do it for 100 iterations, so in that case it will be, you will compute the output for each time. So you will have output here over x, then given the output you will compute the loss between y and yp. Given this loss function, you will compute the gradients with this predicted, with this loss value. Given the gradient, we will update the weights. Okay, so this is, and this we will do for, keep on doing it in iterative fashion, and this till we have a very small value of the loss function, which means that this orange curve will finally take the shape of this blue curve. Okay, now this is how the equations have to be written, but the good thing is that given these deep learning libraries, we do not have to do it manually and we can directly use them to compute it. So here I'll show how to do it with the PyTorch. So this is a simple, this can be seen as a pseudo algorithm. Like these are the steps. First you have to compute the output, you have to compute the loss, you have, then the gradient is computed, and then the weights are updated, and this keep on doing in an iterative fashion. Now using deep learning libraries, we just need to compute the output and the loss value, and rest of these things will be taken care by the library itself. So we do not have to compute the gradient or have to update the weights explicitly. You just have to call a function and this will be done. So let me show an example for that. So here we are using PyTorch, which is a deep learning library, and we are using some transforms which are already defined in Torch Vision. So before starting with this, let me show how the training works. Okay, so what we are doing, we are running it for a certain number of epochs. Here epochs are 10, and this is our data, x and y true. So in our previous example, it was x comma y. Okay. We are getting the output. So this model of x is getting you the predicted output. Okay, so this is similar to that output function. Once we have that output function, we are applying a loss function, and this loss function is already defined in the PyTorch libraries. So we are using here as a cross entropy loss because this data set is a classification data set, and just calling this function with our predicted output and the true output, and the loss value is computed. Given that loss, we are doing a backward pass. So with this backward pass, the gradients are computed, and we are updating the weights by calling this function step. Okay, so this whole thing, which we have not yet completed, we have just written a small framework, can be easily done with only using these 4 steps there. Okay, now let's start delving into these steps in detail. Okay, so here is the thing. So this is basically training a neural network on MNIST dataset. MNIST dataset is a handwritten digit dataset. So it looks like this. There are images on which we have handwritten digits, and they are being labeled with whatever the digit is written. So this first image here, so this though represents like a one image, but it is a collection of, so each this digit is an image here. Okay, so this is basically how many images are there? 4, 8, 12 and 16. So this is a collection of 16 images. The first image is annotated as 7, second image is annotated with a class 2, the third image is annotated with class 1, and so on. So the target here is that given any handwritten image, we have to classify it into one of the classes ranging from 0 to 9. So there are total 10 classes, 0, 1, 2, 3 up to 9. It is a 10 class classification task, and for that we have to, so we are going to do this with a neural network. Now, talking about the inputs here. So in our toy example, we considered an input to be a scalar value. It had only one dimension, right? Just a number. Now, in case of MNIST, each input is an image. So it is a high dimensional input. So the dimension of this image is 28 cross 28. So the size of the input is 28 into 28. Okay. Now, given these images, how can we train a network? So first is we have to prepare the dataset. Okay, so for preparing the dataset, so what are the components? First is how to prepare the dataset. Once data processing is done, what should be the architecture of the model we are using? And the third is the updating the model. So first is what will be the architecture we are using? We are using a simple fully connected network. So this is the first layer, which is taking the dimension input of the dimensionality of 784 with hidden neurons is 128. Then there is a next hidden layer which reduces the dimension further to 64, and the last last layer which reduces the output to a 10-dimensional output, at which we will be using to make the final prediction here. Now for all these inputs, the activation function is a ReLU function here. Okay. Now given this forward self comma x, we will have so how to compute the output of the model. So whatever the input x will be given, the output has to be computed as, first we will flatten the image, so we'll get a single 1D vector. After flattening the image, it will be passed through the first hidden layer, which is self.fc1 of x. So this fc1 is basically a linear layer, so it has both this weight and bias, so it is corresponding to w1 and p1. So self.fc1 of x is here representing the w1 transpose x1 plus p1. Okay, and then applying the activation function of x1. So this expression here is similar to this toy example, this line in toy example, which is this. Okay, and the dimensionality of w is being controlled by this value here. Okay, this is clear. Any doubts so far? Okay, moving forward ahead. Similarly, once we have the input x1, we will then pass it through fully connected layer 2, and similarly apply the same activation function, and we'll get x2 here. Okay, once we have x2, we will pass it to the next layer, and we'll get the raw output, which is y. So just to print the model architecture here is, it has first linear layer, which is taking an input of dimensionality 784, reducing it to a dimensionality of 128. Then second fully connected layer, taking an input of dimensionality 128, reducing it to 64. Then another linear layer, which is taking a dimensionality of 64 and reducing it to 10. And for each layer, the activation function used here is ReLU. Now, The another step is to prepare the data set. So we are using the MNIST data set. This data set is already available to us. We do not have to pre-process it. We will just call it from the torch. So torch.tutors.data.total order has already this data, and from there we are just calling this MNIST. And similarly, so this MNIST data set comes with two split. One is the training split, the other is the test split. So the training split has 60,000 images, which means 6,000 images per class. Similarly, for the test split, we have 10,000 images, which means 1,000 images per class. The model will be trained on this training split, that is 60,000 images, and will be tested eventually on this 10,000 images. Okay. Now the training starts. So for training, we have a model. We have an optimizer. So optimizer is which will be used for updating the weights. So in this we have passed the weights, which are represented by model.parameters here, and the learning rate. So the learning rate is decides how much each weight has to be updated. So the equation is W is equal to W. Let me write the equation here. So the update equation here is for any weight is W is equal to W plus learning rate into gradient of W. Okay. This learning rate controls how much of this weight has to be updated. Okay. Generally, we want this learning rate to be high in the earlier rounds of the training, and then as the training proceeds, the learning rate keeps on decreasing. Okay. So with this, the loss function is this cross entropy loss. So what does this cross entropy loss means? Right. So cross entropy loss says that whatever is the correct class, the probability of that class should be high. So here the output y is a raw output of, so y is a 10-dimensional output. Okay, it doesn't mean anything. So this is called as logits. This is also known as logits. It's okay. Now we will convert it into the probability of each class. So for that we will pass it through y is equal to softmax of 5. Now what will happen is that this 10-dimensional output will be converted into a probability vector where each value will be the probability of that corresponding class. And how that is computed? So that is equivalent to exponent of y underscore I. So I'll just write. So what that softmax of this means that actually this y, let me not call it y, so let's call it y probe. Okay, so the probe y underscore probe. Okay. So y underscore probe of ith element, the ith element of this will be computed as this exponent of y underscore I divided by np dot sum of exp of y. Okay, so once you have the probability for each class, how the loss function is defined. So the idea is that the model should assign the maximum probability to the correct class, right? So the loss function is defined as the negative log likelihood of the probability vector of the correct class. Suppose J is the correct label of this class. So suppose J is the ground truth class. That means that if it is an image of 7, then 7 is the ground truth label. Then the predicted probability for class 7 is what this y underscore prob of J will be representing, and we have to maximize this probability. So our loss function will be negative log of this. Okay, the smaller the losses, the higher is the predicted probability, which is what we desire. So now this cross entropy loss will be doing all these computations and will be giving you the loss value. Once we have this loss value, we will first make all these previously computed gradients to 0, and compute fresh gradients using the backward function. After computing these gradients, we will step to the step function optimizer.step and we'll update these weights and the biases. Okay, and we will keep on doing this. Now, if you want to see the results after each epoch, what we can do is we can predict how many correct inputs are there. So you can see that after epoch 0, the accuracy of the model was 90, which 90%, which means out of 100 images, 90 images were correctly classified. After first epoch, the accuracy increased to 92%, then 94%, and so on up to 97%. Okay, so this is how you can train any neural network easily using all these deep neural network libraries. Just for understanding how this algorithm works, I have provided a basic framework here. You can fill in the missing components, like for example, the derivative of sigmoid, similar from these equations, and then similarly you can compute the gradient for W1 and B1, and then you can use some learning rate here. LR can experiment with multiple learning rates and can fill in these values and can try to see an experiment with it. Okay. So here from this toy example of how to update the weights of a neural network, we have now seen how we can use existing deep learning libraries to implement a neural network for a very high dimensional data, which is like here, though we have experimented with MNIST, but it is pretty high, 784 dimensional inputs, and how to train that model, and also how it is getting, the accuracy of the model is getting improved. Okay, so any questions so far? Any other questions or doubts you want to ask here? Okay, so if no, then maybe we can just stop here, or I can show you how this further certain results on this experiment. So I have also plotted how this misclassified images looks like. So we will now visualize the result of this trained model, and then maybe if you do not have any further questions, then we can end today's session here. So this is for the test loader, that is the test split, which has 10,000 images. In that test loader, all these images for which the predicted class is not same as the ground truth class is being plotted here. Okay, so this is being used using this index, and you can see that these are the images for which the predicted labels are not same. These are the predicted labels, so which means that the class is 5, ground truth class is 5, but it is predicted as an instance of class 6. Similarly, this is an image containing 6, it has been predicted as an instance of 5. For 4, the output is 6. For 6, the output is 0, and so on. So this is where the model has failed, and what are the labels being predicted by the model versus what are its ground truth labels. Okay, but this is pretty doing good. So this is 97% accurate, which means the number of misclassified images are only 3% of the entire test split, which is like 10,000 images are there. Okay, and I have just shown a very small subset of it, just 16 misclassified images, but you can visualize others and can see the result as well. Okay, and one more thing before ending the session is that when we train the model, we can apply certain kind of transformations. So here there is a field for transform which applies certain transformations, and though here I've just used a simple transformation converting it to a tensor, we can actually play around multiple data augmentations and can see it. So we can apply different kind of augmentations like random erasing or resized crop or rotation and blur, and adding these transformations in the data loader can help you in achieving better accuracy and generalization capabilities. These transformations are again available in tensor or torch version, and you can directly look at it. So if you open this Torch Vision site, so you'll find there are plenty of transforms available, and you can play around any of those and try to fit in find the right parameters for your data set and can work around. So like for example, transforms like center crop, where from an image you are cropping the center part of the image, or you are jittering the color of the image. Similar is doing the 5 crops. So what it means that from a single image you will be doing 5 crops, which means the center crop, the left image, the right, the top, and the bottom. Sorry, yeah, the top, the bottom, and left, right. So basically, so the top left, top right, bottom left, bottom right, and the center crop. Then you can have grayscale, converting an image from 3 channels to a single channel image. Padding. This will not be applicable for MNIST because MNIST is already a grayscale dataset. Okay. Then you can pad certain images. You can crop. So though it's a 28 cross 28 images, you can resize it to 26 cross 26, or you can do a random cropping of 26 cross 26. And to keep the same dimensionality, you can pad so that the resultant output is still 28 cross 28. So generally we use this padding with random crop to have the similar input size. Then similarly some affine transformations you can apply to the image, or random applies. Basically you can select a lot of transformations and it can apply all these transformations with some given probability. Random crop, similar to what I just described before, and there are so many, so you can just play around these transformations and try to fit in according to your data set, and that will help you in achieving better generalization and accuracy performance. Okay, so I have not used any transformations, but you can definitely use it. However, make sure that your transformation should not change what you are learning. For example, for these images, random horizontal flip will not make sense. If I flip the image of 6 horizontally, it is not some valid 6 image of 6. So horizontal flip is not valid for this case. Similarly, however, the vertical flip will also have the same issue, right? Flipping 4 to something vertically will not result in an image of 4. So you have to make sure that whatever the transforms you are applying does not change the property of your data images there. Okay. So for example, here I can rotate these images by smaller degrees, but not with a very large degree, of course. Like for example, if I rotate 6 to a very large angle, it might even look like a 9. So if I just change it completely. Okay, so you have to take into account the valid transformations while training the model as well. Okay, so with this, if you do not have any further questions, we can end the session and can meet next Tuesday again on the same time. Okay, then I'll end the session. Thanks for joining. See you next Tuesday.